Hi, my name is Ignacio Delgado and I'm going to carry out the presentation of the paper entitled Attestation Waves, Platform Trust via Remote Power Analysis, which have been recently accepted on the International Conference on Cryptology and Network Security. As an outline of this presentation, we will first give a little introduction, trying to understand why this paper is important. Then we are going to move to see some of the background that we have used to make this paper and to work on the new ideas on this paper. Then we are going to move to the actual content of the paper, trying to understand how we use the remote power analysis for attestation. After this, we are going to study the protocol and the threat model that we are considering in this paper. And after that, we are going to move to the evaluation and the results that we are getting by using this remote power analysis for its use in attestation methods. After this, we are going to see that we have to use some parameterization in order to get a safe enough attestation methods. And finally, we are going to conclude with the conclusions and to see the limitations on this work and the future work that we need to carry out in order to improve this proof of concept. First of all, we are going to give a little introduction to try to understand why this paper is important. To establish platform trust is a need, and classical attestation methods are suitable to this purpose. What attestation does is to verify the integrity of untrusted systems, and normally this is made by computing a checksum from the memory of the device that we are aiming to attest. However, this traditional method has to face some attacks as proxy, memory copy, or rootkit attack. We will talk later a little more about those. Due to these attacks, some studies have tried to carry out attestation using side channel information from the device that should be attested, mainly using electromagnetic emanation. On the other hand, some of the last side channel attacks have been based in remote power analysis. This is, they try to retrieve critical information from a crystal system using sensors already placed in the system on chip. This work aims to merge both ideas by using remote power analysis for constructive applications. What we aim here is to use the information retrieved by those sensors to characterize given operations and perform remote attestation. In a typical software-based attestation, a verifier proposes a challenge to the prover, who has to compute a checksum of its memory content and send it back to the prover, satisfying a request to response time. This method presents several threats. The prover can perform a memory copy attack, which means that he computes the checksum somewhere else. Also, he can forward the challenge to another device, giving place to a proxy attack, or he can hide malicious code in parts of the memory where the verifier is not able to check. To avoid this, several works have tried to use electromagnetic emanation to detect malware or to verify if an execution is honest. Nonetheless, these methods require proximity and physical presence, since we need some equipment to capture electromagnetic emanations. Our proposal is similar to the latter, but using resources already placed within the system running the executions. We don't need to have physical presence, proximity, or external setup to capture side channel information, and we are able to retrieve finer grained information than a simple request to response time. As we can see in the figure, in our case, the prover and the verifier processes are running the same system on chip. What we do is to use an ADC, an analog to digital converter, that captures voltage fluctuations in the power distribution network using direct memory access. The trace containing the information of the voltage fluctuations is stored as binary data and used as evidence in our attestation procedure. For this reason, the ADC is inside the trusted execution environment, the TE, but how this happens in practice depends on the TE technology. Concretely, our experiments are carried out in a Pincus Zeta-1 board that incorporates a Synco 7000 FPGA that we program to activate the ADC on it, and ARM Cortex A9 processor that run the different binaries. The only common element shared by these two entities is the power distribution network that we use to obtain the voltage fluctuations and carry out the process of attestation. In practice, the trace of interest is set for us by using subtriggers that mark the beginning and the end of operations, as we can see in this other figure. This allows us to highlight the region of execution in the trace and to work easily with these traces. One of the strengths of this paper is that we demonstrate how our attestation method can be applied in real-life deployments and not just remain a lab concept. This is done through the use of a protocol that details the communication between all the entities involved in the process. This is an important part of our work since it deals with a problem that is only treated at a high level in similar previous works. This protocol consists of a setup phase where the verifier, the prover, and the measurement tray receive a public-private keeper. Also, it has a trusted launch phase in which the verifier wants to launch a TE on the untrusted platform. For this, the verifier generates a random number together with an identificator A of the program that the TE must execute on the prover. The verifier captures time T1 and the prover calculates a checksum and sends back the result to the verifier. At this moment, the TE is launched and receives a public-private keeper. Then, the verifier captures time T2 from the checksum result, and if the difference between both times is as expected, the verifier is now convinced that there is a TE residing on the untrusted platform. Finally, in the computations phase, the verifier sends a random number and a token to the prover together with the identificator of the operation that he aims to run on the prover. Then the prover executes the operation with the token as input and generates an output and a fingerprint of this operation, while the analog to digital converter included in the TE measures the power consumption from the untrusted part of the prover, getting as many traces as decided by the verifier. This is done by repeating the operation as many times as the verifier wants. Then the TE contacts with the prover, sending an encrypted version of the traces to it, and the prover contacts after this with the verifier that gathers all the traces that he has requested. Finally, the verifier contacts with the measurement tray, sending the traces, and it checks the level of trust of the prover by comparing the traces with the list of templates that it has for that specific operation. Depending on the level of trust obtained after this comparison, the measurement tray outputs a bit, 1 or 0, that determines if the level of trust of the prover is good enough or not. Against the protocol that we have just seen, we consider an adversarial model based on the one that Dolev and Zhao presented on his paper. We assume the presence of an adversary that is able to load programs of their choice and observe their output. Within this threat model, we consider 3 types of attacks: measurement substitution attacks, false result attacks, and application substitution attacks. For the 2 first, the adversary can only succeed with negligible probability due to the construction of the protocol. For the 3rd one, we need to use several traces during our attestation procedure, so the adversary has only a negligible probability to succeed. The risk for this 3rd attack is that a malicious user can use a false positive result from another operation and make it pass the attestation as it is an actual correct trace. For that reason, if we use several traces, the probability of success is highly reduced, since the attacker would need many false positive results, which is not easy to achieve. Moving to the evaluation of the traces, our process consists of the 3 following steps. First, we select the traces captured by the analog to digital converter while the processor is running some given binaries. With those traces, we generate a template by averaging a large number of traces. In our case, we are using 1000 traces. We can see in the figure how the templates coming from different operations present different shapes. Then, we compare the template against traces that belong to the corresponding operation, and also against traces that shouldn't match a certain template, since they come from different operations. As we can see in this other figure, the purple trace coming from the FASTA operation matches perfectly with the FASTA template, while the yellow trace coming from the FEAR operation does not match with the template. We have done here this comparison with our naked eye, but in practical terms, it is done by using Pearson correlation and establishing some threshold values from which we decide if the matching of a trace with a template is good enough or not. Once we have performed such correlations, we can obtain a statistic about the true positive, false negative, and true negative results. From this, we compute precision, recall, and F1 metrics, which are normally used in information classification and give an idea of accuracy and relevance of our experiment. This way, Precision gives a measure of the number of correct results among all the returned results, while recall gives a measure of the number of correct results divided by the number of results that should have been returned. This means that a low result of precision implies that a high number of incorrect results are considered as correct, so our system will be yielding many false positives. On the other hand, a low recall implies that we are not considering as correct some results that indeed are correct, leading then to a high number of false negatives. Finally, F1 is the harmonic mean between recall and precision, and allows us to give an idea of how good our system is at retrieving results with one single measurement. The results from those stats are the following. 35 out of 47 programs show a precision above a 90%. 27 out of 47 programs show a recall above a 70%. This means that our method matches correctly positive results of traces with their template among the total number of traces, coming from corresponding and non-corresponding operations. However, many correct traces are not considered to have a good enough matching with their template. Additionally, some concrete operations are easily confused by others. It is the case of NDES and nettle AES operations, where 8.2% of the traces coming from NDES pass the attestation process for the nettle AES operation. For this reason, we propose to use several traces for one attestation procedure in order to avoid false positive results. In order to do that, we use a training phase in which we determine the probability of a malicious user to succeed with a trace coming from another operation, P alpha, and the probability of a trace to satisfy the attestation running the correct operation by a non-honest user, P beta. With this, we determine by the following formula the number of traces required that should pass the matching with the template to satisfy the attestation method. This threshold can be freely selected by the verifier, and in our case we have selected X threshold divided by the total number of traces to be in the halfway between P alpha and P beta. However, another verifier can set different threshold values. As well, the number of traces n is also selected by the user, and the value of the threshold is determined depending on it. As long as n gets larger, the security level is improved. The following table determines that for our worst-case scenario, with 52 traces is sufficient to achieve a 32-bit security level, which guarantees that the probability of a malicious user to succeed is less than 2 to the minus 32. If we want to improve the security level to 128 bits, we will need to use 243 traces, or 494 in the case we aim to achieve a 256-bit security level. In conclusion, in this work, we have proposed a new method to check the integrity of a system on chip by capturing the side channel leakage produced during the execution of certain binaries. Also, we have shown that the use of an ADC as a sensor to capture voltage fluctuations in the power distribution network is suitable to characterize the operations being executed inside the processor. Additionally, we have shown in this paper a proof of concept of an attestation method that does not rely on request to response time, using instead power consumption traces that we capture directly from within the system on chip, with no need of external equipment or any other software or hardware overhead. This way, this is the first attestation protocol that considers remote power analysis to realistically verify the integrity of an untrusted system. As limitations found in this work and the future work that we should carry out to try to solve them, we can mention that the recall stats are improvable, although we can detect and differentiate honest users from malicious ones by using several traces during the attestation procedure. We need to put some effort to improve results when we try to carry out the attestation using only one trace. Substitution attacks are a real threat. To give a deeper insight to this work, we should consider strategies to modify binaries and see the impact that this has on the traces that we use on our attestation method. Also, the matching of traces and templates is mainly based in the duration of the executed operation. Nonetheless, the fact of using vectorial data instead of an scalar request to response time is beneficial since it hardens proxy attacks. Finally, requiring a TE for dynamic attestation could be paradoxical, since the target binary could simply be part of the TE itself. However, a major goal of TEs is reducing the trusted computing base, and keeping the target binaries outside the immediate TCV significantly narrows the attack surface. Thanks a lot for watching this video, and if you have any question, you can send me an email to ignacio.delgado-lozano@tuni.fi, or you can see my live presentation on CAN's conference and ask me directly a question there. Thank you very much.